So it's a pleasure to introduce our speaker, the last one before summer, and then we will start in September. So is Matteo Levi from Politecnico di Torino, and not erroneously from Bologna, as I mentioned in the email. And he's going to talk about distortion and distribution of sets under inner functions.
Okay, so thank you, Filippo. And yes, this is the title of the talk, and this is something I I worked on during my visit to Universitat Autònoma de Barcelona, which was co-hosting my PhD program together with Bologna, and is a joint work with Artur Nicolau, who was my local supervisor, and Udi, who is his student. And okay, so I will, being the last seminar before the summer, I will try to keep it very soft. So I will do some introduction to the topic, even if I know that most of you knows the subject much better than I do. But yeah, let's see some introduction. So the notation is standard. And so D is the unit disk, and the partial D is the unit circle. And we say that a sequence of points contained in the unit disk converges non-tangentially to a point P in the boundary of the disk if the sequence is contained basically in an angle center at the point P, and in such a case we say that if we have a function defined over on the disk, we say that the function admits a non-tangential limit at the point P in the boundary if the sequence of images of the function along a non-tangential sequence converges to some point in the Riemann sphere. In such a case, we also use this notation to denote the non-tangential limit. So this symbol basically stands for the Stolz angle here, and this means that Z is converging to the point P inside the Stolz angle, so non-tangentially. Okay, and so today we are gonna focus only on holomorphic functions that are mapping the unit disk into itself, and it is very well known that any such map admits angular limit at almost every point of the boundary. This is a very classical result of Fatou. Well, actually, I mean, the result is more general. It holds for all bounded analytic functions, so not only analytic set map, and also more in general for Hardy spaces. And there are a lot of generalizations also about the region of convergence, but this is enough for us today. So we consider analytic self-maps of the unit disk, and we know that angular limits or non-tangential limits, they exist at almost every point of the unit disk. We are interested not only in the existence of such limits, but also in the values that the limit takes. So in particular, we say that the point C in the boundary of the disk is a Fatou point for the function f if the point is mapped again to the unit circle. Okay, so Fatou points are all those points in the unit circle which admits a unimodular angular limit, or okay. Let me also introduce the concept of angular derivative, which is basically generalizing or extended the concept of derivative also at points of the boundary of the domain, so of the disk in this case. We say that the function f admits an angular derivative at f2 point if the following limit exists and is finite. So observe that I mean this is well defined at f2 points, because otherwise this ratio would blow up if the value of the function at z would not approach the f of c. And there are many others equivalent definitions of angular derivatives. They are basically summed up by the well-known Julia-Kara-Theodori theorem, but so they are very useful, and we actually use all these definitions in the papers when we do our theorems, but this is fine for the moment alone. And so I want to stress the fact that so angular derivatives are useful somehow to detect and to classify a fixed point for analytic self-maps of the unit disk. In particular, the following theorem holds. So this is a very classical theorem in holomorphic dynamics, and it's saying that if I take an analytic self-map of the unit disk, which is not an elliptic optomorphism, then there exists a unique point in the closure of the unit disk, which takes the name from the authors of the theorem, such that like all the iterates of the function f tend to the point p uniformly on compact sets, and such that it is the unique fixed points in the closure of the unit disk satisfying these things, so such that the modulus of the angular derivative is bounded by 1. Okay, so basically so the situation is that when I have a function mapping the unit disk in itself, there are basically two things that can happen. So either I have a fixed point inside the unit disk, and in such a case this is unique. Otherwise, I can have no fixed points in the unit disk, but possibly fixed points on the boundary. Of course, like a fixed point in a boundary is fixed in the sense of radial limits. And in such a case, you can also have many fixed points. So in the boundary, it's not necessarily unique, but it's only one, the point which is the Denjau-Wolff one, so which is attractive for the dynamics and satisfies this condition here. Okay, so
Matteo, sorry.
yes.
The first inequality is true only if p is on the boundary. Otherwise, the derivative might be 0, right?
Of course, yes.
You are not assuming right. Other condition.
Yeah, you're right. Yeah, this is yeah, I mean, of course, inside the unit circle, this could vanish, but when the derivative is angular, it's also positive, but almost by definition. Well, by the Julia-Kara-Theodori, it follows from the Julia-Kara-Theodori theorem. Yes, thanks. And okay, so let me define what inner functions are. So a function mapping the unit disk into itself, analytic, is said to be an inner function if almost all of its non-tangential limits belong to the unit circle. Again, so this is equivalent of to say that the Lebesgue measure of the Fatou set of the set of Fatou points of f as full measure in the unit circle. So here lambda stands for the normalized Lebesgue measure. So we're basically, so morally inner function are all those self maps of the unit disk such that the boundary of the circle is also almost mapped to the boundary of the circle. And pretty much by definition, you can see that such a map automatically also defines a map defined on the boundary of the disk at almost every point by means of the value of the radial limit. Okay, so with maybe a slight abuse of notation, I still write f also for the boundary function, which is mapping, which is defined almost everywhere on the boundary and is mapping the boundary to the boundary again. Okay, this is really like the object we are focusing on. So it is this map, and as we will see, like these maps are maybe not so easy to handle, but I will explain better later why. Before, let me give you like some introductory useful result on inner functions. So an example of inner function, well, the prototypical example is given by Blaske products. So yeah, probably everyone knows, but like if you take a sequence of points in the unit disk such that they approach the boundary, say fast enough, so that this sum converges, then the Blaske product B of Z is defined by the following infinite product. So this is basically a product of all. I'm taking the product of all these automorphisms that are switching the origin with the points of the sequence, and yeah, it can be shown that this is an inner function, and this is for sure the main way to construct inner functions. There is a second way to construct inner functions, which is the following. So very different. So you can take a measure mu, which is positive and singular on the circle, and extend it inside the unit disk by means of this Erglot's transform, and then take the exponential. Sorry, this I forgot to write, but this is just a unimodular constant to possibly rotate the function. Okay, so any such a function is called singular, and it's also inner. And pretty much there are no other examples of inner functions in the following sense. So there exists this classical factorization theorem, which is saying that every inner function f can be written in such a way, so as the product of two terms. The first one is b. So with b is basically the Blaske product constructed over the sequence of zeros of f. Okay, note that I mean that the sequence of zeros of f must satisfy this condition, otherwise it would accumulate. And okay, sorry. So this is the Blaske product on the zeros of the function f, and this is just well, a term to account the zeros in the origin. And S of mu is a singular inner function. So every inner function has this form, and also, so Blaske products are prototypical examples not only in the fact that they are building blocks in the following sense of inner functions, and they are somehow, so this term is summing up all the information contained in the zeros of the functions, while this function is clearly zero-free by definition. But also, Blaske products are prototypical in the sense that basically every inner function is a Blaske product up to composition with a disk automorphism in the following sense. So this is also a classical result by Frostman, which is saying that if I take any non-constant inner function, then at all the points of the unit disk, but possibly the ones belonging to a set K of logarithmic capacity 0, if I compose the function with a disk automorphism in such a way, then I obtain a Blaschke project. So, I mean, it's a good practice when working with inner function to think to Blaschke product, which are easier, and it's not such a big loss of generality, let's say. Okay, so let me move on. I want also to say a couple of words about Clark measures. So Clark measures are a nice tool when working with inner functions, and I mean, maybe they're not so well known as they would deserve, I would say, and that's the definition of Clark measures. So let's start with a function f mapping the disk into itself, and fix a point in the unit circle A, and then construct the following function. So we take the ratio of alpha plus f of z over alpha minus f of z, and then we take the real part. So it's easy to see that this function is it's clearly harmonic, and it's also positive. And so we know that by the Ritz-Erglotz, I think it's called, representation theorem, we know that any positive harmonic function can be written in this way. So it can be represented as the Poisson integral of a measure mu, which is finite and non-negative on the unit circle. So here I write mu of alpha to denote the dependence from this point alpha that I fix in the circle. And so the family of all such measures, while alpha runs, with alpha running in the unit circle, is called, any such a measure is called, in this family, is called a Clark measure for the function f. And actually, Clark measures, they can also be, I mean, they are useful in many ways, but they can also be used to characterize inner functions. So inner function have a definition in terms of Clark measures, which is the following. So a function f is inner if and only if the associated Clark measure is strictly singular for some point in the unit circle. If it is for some, it is for all. So it's not important which point we choose. So this theorem, I'm not sure who is the author, but I think I read it in some for the first time in some notes by Eero Saxman, and but yeah, I don't know who is the original author, to be honest. And actually, we can even be a bit maybe more precise. So what? Okay, this singular measure is actually fully supported in the points which are in the preimage of the point alpha parameterizing the measure with in the preimage with respect to the inner function f. Okay, so now I'm gonna come soon to our results. Before, so now I go back to our object of interest, which is this function in the title. So, as I said before, we are interested in the boundary function induced by an inner function. So, as I mentioned before, these functions, they do not enjoy the same regularity as the inner function f itself. in a sense that I will clarify soon. So take a function f inner. So here it's already written in terms of its factorization in a Blaschke product and a singular in a function. So we call singular point for the function f any point which is lying on the boundary of the disk at which the function cannot be extended analytically. Then, okay, this equal is not a definition, this is a theorem. So it's a classical theorem. It can be proved that the set of singular points for the function f is exactly equal to the set of accumulation points of the zeros of the function f's plus the support of the singular measure coming from the singular factor here. And these points are exactly the points like creating a bit of troubles when studying like these kind of functions. In which sense? So let me give you this theorem which clarifies a bit what I mean, saying that these points they create troubles. So basically I mean that close to these points the behavior of the function is highly chaotic. So for instance, the following theorem holds. This I believe it's by Garnett. So if I take an inner function and C0 a boundary point, then I have the cluster set of the function at the point C naught is the full is the closure of the unit disk. So the cluster set of an inner function is basically the set of all those points in the Riemann sphere that can be reached by a sequence, by the images along a sequence of points in the unit circle approaching the point xi naught. Okay, so are like all the possible images of f at the point xi naught, where the image is attained like following like all possible different paths converging to the point xi naught. So basically, I mean the function f at the point xi naught takes every value in the unit disk. Under this point of view, like following the same stream of thoughts, we can consider not the function f and these kind of paths like contain the unit disk, but we can consider like this boundary map from the circle to the circle, and we were able to prove the following, let's say, I don't know, irregularity result, or it's sort of a 0-1 law saying that if I take an inner function, so and the point in the unit disk, so either the point is not singular, so the function behaves very, very nicely close to the point, so it can be extended analytically around the point, or the point is singular, and in such a case, even if we consider a very, very tiny arc centered around the point xi naught, the image of such an arc spans is the full unit disk. And these results, actually, we proved the result using Clark measures. So that's also why I introduced Clark measures to you. Okay, so we understand that these maps are not so easy. So it's for example, if we take a set containing the unit circle, and we want to understand like where is mapped this set, or more precisely, which is the pre-image of this set under the action of an inner function. This is not an easy task because, yeah, I mean, you have you have that close to these kind of points, you go pretty much everywhere, and it's very difficult to keep track of the shape of the set under the action of an inner function. However, you can still keep track of the size of the set. So how much the size of the set is changed containing the unit circle is changed under the action of an inner function. So in particular, there is this super classical, I mean super old at least, theorem by Loevner, which is saying that if I take an inner function which is fixing the origin and a set E in the unit circle, then, I mean, however crazy the preimage of this set can possibly be, still the Lebesgue measure of the set E coincides with the Lebesgue measure of its preimage under the action of the inner function. Okay, and okay, this is the original result by Loevner. Now, if we instead introduce now the concept of harmonic measure, so okay, everyone knows, but just recall that the harmonic measure of a set is just the Poisson integral of the Lebesgue measure integrated over the set E in the unit circle. And of course, if you put 0 in place of Z, you recover the Lebesgue measure. Okay, so basically this result by Loevner can be rewritten in terms of harmonic measures in this way. So this is an easy exercise, and it's a slightly more general version of the theorem. So if we put the harmonic measure lambda z here and the harmonic measure at the image here, we can drop this assumption that the function fixes the origin, and the theorem still holds true and reads like this. Of course, okay, of special interest is the case when z is fixed, and so if the z is fixed, it reads even nicer, because we have the same measure on the left and on the right, so we are really like comparing the very same thing. And so we can say that if f fixes the point z in the disk, then the harmonic measure at z is invariant under the action of the inner function in this sense. Okay, so many years later, after Loevner, so some other authors, they basically reconsider like this kind of problem. So this kind of quantitative analysis on the size of sets in the circle under the action of inner functions, and they decided like to push forward this analysis and at a finer scale, and to consider what happens if instead of a measure here I put, for example, an Hausdorff content. So let me recall you briefly that what the Hausdorff content is. So I take a Borel measure on the unit circle and a number in between 0 and 1. Then I can define this general mu alpha Hausdorff content of a set E in the unit circle to be the following thing, to be given by the infimum taken over all open covers of the set E by means of open arcs, and is attained summing up the measures of such arcs to the power alpha. Okay, so I mean the classical Hausdorff content that usually we study is the one when this measure mu is the Lebesgue measure, and so that this term mu of I of j is just the arc length of the arc. Okay, so in 1992, Fernandez and Pestana, they basically reconsider the Loevner theorem, but in terms of Hausdorff contents. And okay, again, they stated and proved the result only for inner functions fixing the origin, like Loevner, but again, by means of an easy exercise of conformal invariance, you can rewrite the theorem in this way. And the theorem reads as follows. So I take an inner function, any point in the unit disk, and a set in the circle as before. And we have a similar result as Loevner, but this time we have an inequality, which is saying that the Hausdorff content with respect to the harmonic measure at Z of the preimage of this set under the action of F is bounded below by the Hausdorff content on the set itself times a constant only depending on alpha. Then actually, I mean, they also wrote a full paper a few years later on the value of this constant, but this is, I mean, we don't want to talk about this now. We are fine with any constant here. Okay, so they proved the following, and I mean, again, this result is of particular interest when Z is fixed by the function f. Because if f is fixed, then I have the same Hausdorff content left and right. But the problem is that, well, not the problem. So this is where our this was our observation where our work started. So the fact is that not all functions, as I was saying before, not all inner function they have fixed points in the unit disk. So as I was saying before, when I was showing you the Denjoy-Wolff theorem. So some inner function, they only admit boundary fixed points. So they only fix point on the unit circle. And it's clear that, I mean, this result is not saying much for those functions. Well, actually, it's not saying anything for those functions because, yeah, I mean, it does not even make sense to center the harmonic measure at the point on the boundary. Okay, so basically, our scope was to find similar results but suited for inner functions fixing points on the unit circle and not inside the disk. And I mean, these functions, you don't have to think to something very exotic because there are very easy functions like this one that are inner, but only have fixed points on the boundary. Okay, so for instance, this function has only two fixed points, which are 1 and -1. It's a very easy function, and 1 happens to be the Denjoy-Wolff one because as derivative modulus of derivative is 1, while if you calculate in -1, if I'm not wrong, is 9. And so of course we wanted a theory of this kind and of Loevner kind, which also applies to these kind of functions. We don't want them to be out of the theory. And yeah, I mean, probably, I mean, this is a very easy example. Probably there are also easier examples. This is just the first one it came to my mind. Probably there are easier ones. And okay, so what to do? So it's clear that we have to change a bit point of view because, as I was saying, we cannot use the harmonic measure anymore. So what we do is to introduce a new measure which allows to measure sets also from a boundary point of view, and is the following. So actually this measure was appeared already in a nice paper by Döring and Magnier, which is published in some Brazilian journal. It's not very easy to find on the internet, but it's very beautiful. And they already like use this kind of measure. And we also use the same kind of measure, and which is the following. So P now is a point that can lie not only inside the disk, but also on the boundary. And we define the following measure. So E is a set in the boundary, and its P measure is given by the integral over E of this kind of kernel. So Xi lies on the boundary, and P is the point that I fix, which can be either on the boundary or not. Okay, so which kind of measure is this? So a few things are easy to notice. So first of all, if P lies inside the disk, it's easy to see that this is nothing but a rescalement of the harmonic measure, because I'm basically just erasing the numerator here of the Poisson kernel. On the other hand, if P lies on the boundary, it's clear that this measure is not finite, because of course when the point C approaches the point P, this integral is blowing up. But this is not weird, and is perfect. I mean, I'm perfectly fine with having a non-finite measure, even because there is the following natural interpretation of this measure. So maybe look directly at the last line here. So this measure is basically it can be realized as the push forward of the Lebesgue measure on the real line. So this modulus is just the Lebesgue measure on the real line via this function WP, which is just the conformal map, which is mapping the unit disk to the upper half plane, the one sending P to the point at infinity. Okay, so actually the mu P measure of a set E is really like the Lebesgue measure of its image through the conformal map mapping the disk to the upper half plane. Okay, so this is the measure we would consider, and these are the results we obtain. So the two results, they read, so the first one is a generalization of the result by Loevner from 1923, and this is a generalization of the result by Fernandez and Pestana by 1992. They read similar as the original ones, but but in both we have an extra term. So let's read them through. So again, I take a function f inner. I consider P to be if a two. Well, okay. So the result holds true also for P inside the unit disk, but when P lies inside the unit disk, one can see, it's not difficult to see that this expression and this expression, they reduce, this reduces to the Loevner result basically, and this reduces to the Fernandez-Pestana result. So they are completely coherent. So I am stating the result only for the point P lying in the boundary, which is what was missing from those results. So if the point P is a F2 point of the boundary, and E is a set containing a boundary of positive measure, then we have the following. So the mu P measure of the preimage of the set is equals the mu measure centered at the image of the point times these distortion terms in which is the modulus of the angular derivative of the point P. Okay, so in particular, if P is a fixed point in the boundary, so for example, the point 1 of the example I was giving you before, then we have the same measure here and here. And this basically the same things happen with the Hausdorff content. So we have the same bound on on the Hausdorff content of the preimage of the set in terms of the Hausdorff content of the set itself. And here again, we have a distortional term, which is again the modulus of the angular derivatives to the power, to this power alpha. So I'm not giving any proof of the results because I think yeah, I mean, I already gave some stream of ideas, and well, the proofs are a bit technical in the sense. So the idea is simply to take a sequence of points inside the unit disk approaching the point P, and basically so do results for the unit disk and then push these results to the unit circle. And the proof is a bit technical because you have to control many quantities that do not blow up, and that the limits everything pass to the limits and so on. But it's not like, yeah, there are not big ideas in the proof itself. And what instead I prefer to maybe mention are a couple of application theorem that we got out of this. So one is this funny application. So let's take E, a set in the unit disk this time. So E is not in the boundary of the disk anymore. This time E is inside the unit disk. I denote by E and T the non-tangential closure of the set. So by non-tangential closure, I mean the following are all those points lying on the circle that can be approached non-tangentially by sequences of points like containing the set E. Okay, so of course, if the set E is just like fully contained in the disk, this is an empty set. But you can think to many funny sets like having some points being tangent internally to the unit disk in many points, and this is the non-tangential closure. And basically, we have the following application. So this is an estimate of the size of the set of omitted points of an inner functions in terms of points having infinite angular derivatives. So we take a function f mapping being inner, and we denote by E the set of its omitted points, because inner functions, I mean, they map the disk to the disk, but they can omit some points. So in general, they are not surjective. So in general, there is this non-empty set of omitted points. And if we take P to be any Fatu boundary point of F, and alpha to be any dimension between 0 and 1, then there exists a constant depending only on alpha, such that we can bound the Hausdorff content with respect to our mu P measure of the sets of points in the boundary at which F does not admit a finite angular derivative. We can bound it with the Hausdorff content of the non-tangential closure of the omitted points. And again, we have the usual distortion term here. Okay, so this application is, I mean, because in the literature you find other estimates on the size of this kind of sets. So this goes like in this direction. And actually, the proof is also quite nice because yeah, there is a nice application of the Rouchet theorem that we study. At least I studied it in complex analysis, and then I never use it anymore. And while here you use it, and it's nice. And the second application is the following. This is just a version of the Loeffner classical result and of the Fernandez-Pestana classical result for inner functions of the upper half plane. So inner functions of the upper half plane are exactly what you expect to be. So our functions mapping the upper half plane into itself and admitting, okay, now there are, instead of radial limits, we have limits along vertical segments approaching the real axis. So the real axis is mapped almost everywhere to the real axis. And in particular, if we consider those upper half plane inner function that's fixing the point at infinity, then we have that we can prove that the Lebesgue measure of the preimage of any set A in the real line equals the Lebesgue measure of the set itself times this distortion term. So note that here I'm not using our μp measure. I'm using just the standard Lebesgue measure. And so in the case of the circle, we did not have any distortion term here. So it was the classical Loevner result. But in the case of the upper half plane, also for the classical Lebesgue measure, you have a distortion term in terms of the derivative. And also, similarly, we have a Fernandez-Pestana type result for inner functions of the upper half plane, which is saying that the Hausdorff content, I mean the standard one, so with respect to the Lebesgue measure of the preimage of a set, A is bounded below by the Hausdorff content of the set itself, times again this distortion term. And I think I can stop here. It's still maybe 8 minutes to run, but I can stop here. I'm done.
Thank you very much, Matteo. Okay, are there questions?
May I have a couple of questions?
Yes, Pavel.
Oh, Matteo, could you please show this theorem about where the derivative at the point P, at the boundary point, appears? I think it was, yes, the previous slide, yes, this one. Yes. But so this derivative can be actually infinite here, right?
Yes, yeah, that's true.
So even if this set E has a finite measure, in this sense, this mu f of p, the preimage can have an infinite measure. But if it is finite, does this theorem imply the same equality for the case when this first measure in the line up, it says that if mu f e of E is greater than 0, but if I guess that you can allow this to be 0, right? If the angular derivative is finite.
Yeah. I mean, okay, so if this is 0, this is also 0. This is written here.
Yes, I have not seen, but thank you.
Yeah.
May I ask also a question about
to finish? So if this is actually like covering all the cases I didn't say. So if this measure is 0, this is also 0. Okay, so in this sense, even if this is infinite, okay, so the convention is that 0 times infinite is 0 in this sense. And if this is infinite, yeah, so if this is infinite, basically this is also infinite if this is positive, and this is 0 if otherwise. Yeah, that's the full spectrum. Yeah.
Okay, thank you. But could you also show at the beginning there was one slide about composing inner functions with automorphisms?
Yeah. I think it's here.
So, so you work with here is a post composition, right?
Yes. Yes.
So in a sense, if we think about these singular points, you can basically say that singular points are. Is it true what I think now, that the singular points can be thought as limit points of those points Zn in the unit disk where the value equals W? Or maybe you have to apply the automorphism as well.
Could you say
because what is said here that if you choose W for suitable W's, you don't have the singular part, right?
Yes. Yes, I agree. Yeah. Exactly.
And then in some sense, you can write the set of singular points on the unit circle just using these solutions of the equation f of z equals W, right?
F of z equals W. So in this,
so there will be zeros of f W.
Yeah. Yes. Yes.
But
it's true. So in this,
is it known anything about the precomposition? If we take a precomposition with automorphisms, or maybe it does not change anything. You still have the same Bляшки product in.
So you mean?
So when you take f of
for a general inner function or for a Bляшки product?
For a general inner function, of course. The Bляшки product, I guess, just you just move the zeros, right?
Yeah, exactly.
I think it doesn't change anything.
Mm-hmm.
Yeah.
I see.
Sure, stable.
Thank you very much.
Thank you. Matteo,
Thank you.
I have a question, but it's more what happens, or maybe, does it make sense to assume that the inner function is slightly more regular and obtain better results? Or what is the minimal condition for which an inner function extend somehow regularly to the boundary, better to the h infinity, to the infinity condition?
Well, I mean, you have to look for inner functions having no singular points in the boundary, or very few singular points.
Because as soon as they are continuous, they are regular, say.
Yeah.
Okay. And maybe there is even some weaker condition that implies regularity.
Yeah. Yeah, I don't know. I mean, I cannot think of. So for instance, if you restrict your attention to Bляшки products, so you only have the only really problematic points are the accumulation points.
Right.
The zeros, for example. And I mean, so in this sense, you can pretty much construct an inner function with like prescribed problematic points as you want.
Mm. Okay.
I mean, you can even choose only one problematic point.
Yeah.
Yeah.
Okay. Thank you.
Other questions? So Matteo, I have one. Can you show the slide where you have both your result and the previous one on the behavior? I mean, the singular point and the limit. When you restrict the value of your function to a singular point on the boundary, then you get the measure is, I mean, the image is the full disk. The slide.
Yeah, it's here. Here it is.
Okay, good. So my question is, what in between the two results, in the sense that now if you go just allowed to go tangentially to the point, but inside the disk,
Yes.
what do you get?
Well, actually, here in this result, tangential approach is allowed.
Yeah, I know, but I'm saying that now you just exclude all non-tangential approach, so that you are mostly, well, in a sense, near to your result, but you are not really moving somehow on the boundary, but tangentially.
I see. I don't know. So you are asking if maybe this is true also, like only for tangential paths, maybe.
Yeah.
Or if there is a result in between. I don't know, actually. I don't know. This is a good question. I think I don't know. I would bet that this result holds true also for if you assume this sequence to approach the point non-tangentially. But I don't know, actually. This is just a vague impression.
So I mean, all singular points you don't have, in all singular point you don't have any non-tangential limit, or can be.
But may I interfere? I'm sorry, but singular point means a point where there is no holomorphic extension, right?
Yeah.
So if we go tangentially, and if this point, for example, FA2 point, then non-tangentially, then we will have this.
The limit exists.
Yes, the limit would exist, right? So I guess that non-tangential approach is essential here.
Yeah.
You mean tangential approach to get the result? Yeah.
Yes. So there should be also allowed. Yes.
Yeah, sure. No, in fact, my question was in general, if you can say that maybe there are cases where you go in tangentially. What I would expect is that if you consider just tangential sequence, you will get the closure of D in most of the cases. But I don't know. I was just that was the question.
Yeah, but I don't know. Yeah.
Okay, thank you. Other questions? Okay, so if not, we thank Matteo again